Hello, I am Tulan Akbulut, a master's student supervised by Emre Uğur from Boğaziçi University, Istanbul, Turkey. This video is about our recent paper, ACNMP, Skill Transfer and Task Extrapolation through Learning from Demonstration and Reinforcement Learning via Representation Sharing. You can visit our presentation in the main section for more details. You can find the code and data on our project page. Learning from demonstration is a powerful method to teach robots dexterous skills. However, the performance of the robots depends on the demonstration distribution. If the model is requested with the black dot to perform the skill within the demonstration range, it generally succeeds. However, when the system is queried outside of the range it was trained for, the generated trajectories may fail. In this work, we study following challenges in task extrapolation and skill transfer. The relations between task parameters and the required policy are often highly nonlinear and complex in real-world problems. Therefore, excessive policy updates may be required for adaptation. Another challenge is preserving demonstrated behaviors during adaptation, because these behaviors may include intrinsic features that are difficult to encode in a reward function, such as safety, robotic environment constraints, or other user preferences. For example, it may be preferred that the trajectory stay away from the obstacles, even though the reward function does not encode this behavior. The skill transfer between robots with different embodiments is another important problem, because direct policy transfer is not possible due to morphologic differences such as different joint numbers and structures. In literature, state-based correspondences are sought to transfer the policy, but this approach requires additional efforts that pair states of robots beforehand. We propose adaptive conditional neural movement primitives to address these challenges. We use conditional neural movement primitives as the base LfD model, which is pre-trained using demonstrations. In order to achieve the goal with given task parameters, CNMP model is conditioned with the task parameters and generates the required trajectory. The generated trajectory is given to robot execution. If it fails, the reinforcement learning agent is triggered. The RL agent is initialized with the LfD model. The RL agent updates its internal parameters via RL-guided actions, which is alternated with error-based supervised learning based on the demonstration set. This simultaneous training method increases sample efficiency and ensures that found solution is encoded into the right spot in the same latent space with demonstrations, and it preserves demonstration characteristics. After the RL agent finds the optimal trajectory for the new task, this new trajectory is regarded as a new demonstration and fed back to the LfD system. In skill transfer scenario, both robots have their own ACNMPs and they form a common latent space during learning from demonstrations. Then skill transfer for a novel task can be achieved regardless of morphological differences, and it can be perfected using the RL agent. We adapted this experiment from Stark et al. To evaluate our model's adaptation capability to different goal points in a simulated pushing task. 9 demonstrations are provided to a 3-dog planar robot. Then the robot is requested to push the black obstacle to a novel goal point. Blue shows interpolation, red shows extrapolation goal points. Consider extrapolation case as an example. You can see 9 demonstrations on the left and our model's performance before and after RL training on the right. We observed that our model finds the successful trajectory or requires small adaptation for all interpolation goal points. For the extrapolation goal point, it requires fewer samples to adapt than Stark et al. We adapted this experiment from Everton et al. To test our model's adaptation capability in a different setting. The aim is to produce a trajectory that starts from the fixed blue point, avoids the randomly positioned wall, and ends at the randomly selected red goal point. Demonstrations are given for 30 environments. The example demonstrations are shown on the right, and the performance of LfD-only model and ACNMP is shown on the left. As shown, while both methods are competitive in terms of the environments used, ACNMP outperforms Everton et al. When the number of sample trajectories is considered. This experiment aims to evaluate the transfer learning capability of ACNMP. We adapted this experiment from Gupta et al., where robots with different morphologies are provided with process skills to learn how to transfer policies. Given that 3D growth robot has the skill to achieve a button pressing task, 4 of robots should benefit from this experience and acquire the skill in several iterations. Using demonstrations of proxy tasks shown on the right, common latent space is formed. As shown, 2 ACNMPs are able to map 12 demonstrations to the same latent representations. ACNMP and Gupta et al. Are competitive in terms of policy iterations, but our approach finds the common latent space at policy level opposed to state level, therefore does not require additional state pairing techniques. The effect of common representation and reinforcement learning is shown here. For the robot almost acquires skill after transfer, and RL agent is used to perfect it. We also tested our model's task extrapolation capability with real robots in a pick and place task, where task parameters are object and wall height, and in a water pouring task, where the robot learns to pour desired amount of marbles in 18 iterations. We showed that ACNMP is more sample efficient than the state-of-the-art methods, preserves demonstration shape, and enables skill transfer between robots with different embodiments. Thank you.